let's start. First of all, we'll introduce ourselves because we're not like that well known like Elon. So we're going to tell you who we are. My name is Dan Luca. I'm a Java architect and tech lead in Globant Cluj. My main focus is server-side currently, using Java Web Services and scalable deployment. Also worked in a bunch of different hats like Fullstack developer, DB admin, mobile developer, build engineer, anything needed to develop and ship a product. And I'm going to let Andrei say something as well.
Hello, everyone. I'm Andrei Draghia. I'm also Java architect in Globant. I'm mainly coming from the eCommerce space, also currently working with Java mainly on the server side part. In the meantime, I'm also doing some Python, some Ruby, some Go, working with a few different languages across the board, basically doing whatever is needed to deliver different products with the best technology.
Okay, so let's see what we're going to talk about today. First, we'll talk about how underutilizing your hardware is a waste of money, obviously, and why sometimes it's more difficult than you think to fully utilize your hardware. Next, we'll look at what tools we have available for coding multi-threaded apps and what Project Loom brings new to the table in this space. In the second half, we'll see how Project Loom is used in practice. We'll see some results from our experiments, and at the end, we can draw some conclusions. So first of all, using your hardware to the max should be easy, but in reality it's not, because you have all this stuff you have to wait for. So first of all, is Project Loom a free lunch? And what do I mean when I say free lunch? Let's see in the next slide. So there's a famous article written in 2005 by a guy, Herb Sutter, called "The Free Lunch is Over, a fundamental turn towards concurrency in software." What he means when he says free lunch is that most apps were single-threaded apps, and they would benefit every year by an increase in clock speed of new generation CPUs. So it was like a free performance lunch, in the meaning that without any code change or dev effort whatsoever, apps became faster and faster and as time went on. But in 2005, this was starting to slow down, and Herb predicted that concurrency is the next major revolution in how we write software. And you guessed it, the article is so famous because he was right. So here we can see a more up-to-date chart, still not to present, but it's whatever I could find from Stanford CPU DB. The CPU clock hit a wall at about more or less 5 gigahertz. So the next step to improve performance was to add more cores. But we also need to write code in a way that takes advantage of those extra cores. Otherwise, they're useless. So you have more cores now, but you have things, so you have to write multi-threaded apps because you have more cores and you want to take advantage of them, right? But in real-world apps, you also have I/O, which makes threads wait. I/O stands for input-output, by the way. I hope everyone knows that already. So you can have a million sockets open for I/O operations, but only a few tens of thousands of threads. This leads to inefficient use of compute resources, increased cost, and electricity consumption. So it's a waste. You waste money on underutilized hardware. So what can you do about it? Well, you can write more complex code. There are advanced libraries and frameworks that can take better advantage of the hardware you already own, but they are fairly complex, hard to debug, and require additional development training to use. So you have to spend more money on dev training and debugging. So you can kind of pick on how you want to spend your money, either on wasted resources or on developer training. But it would be very nice if there would be a solution that gives you better hardware utilization without overcomplicating the development process, that is writing code and debugging. So let's see if Project Loom is that silver bullet we're talking about here. So let's see next what tools we have now. And I'm gonna let Andrei continue with this part of the presentation.
Yeah, thank you, Alex. Okay, so yeah, I'm gonna spoil for you that Project Loom is apparently kind of a silver bullet. And what I'm gonna talk next before that is to put some context around Project Loom. So we're gonna go through some basics and some theory, and we'll see some other threading models, like what other things are there, and then we see, okay, Project Loom, what it is, which of this threading model it's actually implementing behind. So first of all, let's talk about concurrency versus parallelism, right? So concurrency means that we have multiple tasks and we have only one computational resource, let's say, and we need to schedule all those tasks on that computational resources, right? So basically, we achieve this by doing context switching. So concurrency means that we deal with a lot of things at the same time. By saying that a system has good concurrency, it means that it can handle a large number of tasks per a certain unit of time. Now with parallelism, it means that we have one task and multiple computational resources, and basically we want to split that task across the computational resources to make it faster. In simple words, basically we do a lot of things at the same time, right? Here, a performant system in terms of parallelism means that it can do things faster, right? The latency of that system. We also have an interesting theory in IT here. It's a very simple formula, elegant one called Little's Law, which can give us the level of concurrency of a system, right? So basically it's throughput multiplied by latency. The lambda is the throughput, and basically it means how many requests can our system process, and W is the latency, how fast it can process each of that task. Okay, so let's see how we achieve concurrency at the moment, right? We use threads. So what's a thread? It's basically similar to a process, but it has its own register and stack. It's sharing with the other threads in the process. It's sharing the code, the data, and the files. Now, because those threads have to be implemented by the operating system and have to work for all the languages, they need to make quite some worst case scenario assumptions. Like, for example, what should be the size of the stack? So as a result, they're gonna decide on a very large stack, megabyte size, it's fixed, you cannot really change it. Also, how those threads are basically working in the background, if you remember from school, is that the operating system is scheduling your work on, basically scheduling your threads to the CPU and saying, okay, now you thread execute, now you execute, and so on. This is usually depends from kernel to kernel, how this is implemented. Some are more performant, some are less, but usually they need to do some jumps from user space to kernel space, and this usually takes more than a microsecond usually to do this kind of switching. Also, this kind of switching, it's called preemptive. So the operating system doesn't really know when your thread can actually be stopped and something else to continue. So it's just stopping it just in case, allocating the CPU to some other thread, and so on. Right, so preemptive scheduling. Okay, that's some basic. I hope I didn't bore you too much. Let's see. So we have a few threading models. Probably there are others. Very simple, single-threaded, right? So in our application, one thread. We multi-threaded, and usually with the thread pool. It's the most common use case. We have the fork join thread pool from Java. Then you have other things like the event loop, right? From JavaScript, you can have the LMAX disruptor. It's another quite interesting threading model. You can Google it afterwards if you like. Reactive programming, the hype nowadays. We have things like using the async await coroutines, right? Like you see in Python and Kotlin, for example. You have userland threads, as you see in Go, for example. So let's take each of these and just have a more high-level discussion about them. Single-threaded, very simple, how most of us learn to code, which basically means that the thread is doing tasks one by one, then it's waiting for some response, then it's doing other things, right? As in the picture seeing here. It has no concurrency at all, pretty much. So no concurrent memory access, no headaches. Basically, how fast you can finish your tasks, that's pretty much your level of concurrency, right? Since you cannot handle too many other things. Why I'm mentioning this? Because some databases, for example, are using this kind of model to achieve quite efficient processing. Now, let's do some comparison of those threading models and let's see how they fare against each other. Quite subjective, so feel free to contradict me. How we're going to compare them, we're going to talk about the throughput. So for single-threaded, quite clearly, it can handle one task. Parallelism, right? So let's see, okay, this threading model, how much it facilitates parallelism. In our case, none or low, like you can create multiple threads in your application to run different sides of different parts of the code. It's quite easy to understand, development experience quite straightforward, same for error handling, debugging, profiling. All the tools were basically built for this kind of threading model. Now let's see multi-threaded. So basically, it means we have, with the thread pool, it means we have multiple threads, all of them with pretty similar characteristics, all of them grouped in this thread pool. Then basically the tasks are taking a thread from the thread pool, executing itself on the thread, putting the thread back in the thread pool. So this already, I mean, this is how most of the servers are working. I bet most of you are familiar with this threading model. And as you know, it brings a lot of headaches usually where you have race conditions, where you have things like thread local leaks, right? Especially the Java folks. It's also quite problematic with cancellations. This is not something you encounter that often, especially with servers. But if you try to call an interrupt on one of the tasks to cancel it, you have a good chance that you're actually going to cancel the next task, right? So you're having this kind of issues that can appear with the thread pool. So basically, the throughput is that we have tasks per thread. Parallelism is quite good. It's, I would say, still easy to understand, a good development experience. I mean, most of us, especially in Java, have grown to use thread pools and this multi-threaded model for quite some time. From debugging perspective and profiling, I'd say it's a bit more complicated. Tools have evolved lately, but yeah, it's not, it depends on what tools you're using. It can be more easy or less. Still, you need to use more brain power for it. Going to the next one, fork join pool. Basically here, it's the thread pool model plus divide and conquer algorithm, plus giving the control back to the threads. So here the task is not taking or choosing the thread, or I mean, taking from the thread pool the thread where it's going to execute, but it's basically the thread which takes that specific task. So how it looks, it's basically each thread has a double-ended queue in front of it. All our tasks are going to be submitted to those double-ended queues. And each thread is going to execute task by task from its queue until it's done. Now there's a catch here. Those threads can steal, right? So if a thread is faster and finishes all the tasks from its queue faster, it can go and consume other tasks from the other threads. This kind of model increases the efficiency, and increases the concurrency ultimately, especially for IO-bound operations. Sorry, for CPU-bound operations. If you're working with IO, and usually most of those tasks are IO-bound, then it doesn't really improve that much. So it's not very friendly with blocking code. Okay. So basically, it performs a bit better than the standard thread pool for some cases. It's a bit more complicated to understand, and usually the development experience, it's a bit average, I would say, in the sense that you have different interfaces you need to implement. You need to structure code in a certain way to be able to use this fork join pool model. Same for the error handling, it becomes a bit more difficult. Nothing impossible, of course. Going forward, the event loop. basically, we're back to one single thread. And here the magic is that they say, okay, let's use one thread and let's remove all those idles and waits of the thread. Let's make this thread work to the max, right? And basically what it is, it's a while loop, infinite while loop that keeps taking tasks from a queue. You can just imagine it like this, like a very simple model, right? You have a queue with tasks, while loop, just keep boom, 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 taking task after task. When it encounters a task that has an IO operation or a sleep in it, it's just going to use some very interesting things from the operating system, non-blocking operations, right? And basically delegates to the operating system saying, hey, let me know when this is done, so I can resume this task, right? Again, it's specific from kernel to kernel what those instructions does, but fortunately for us, it's all taken care by the language. Of course, this threading model comes with other issues. Callback hell, lost context. So if you try to log something, you don't really know what was the full context of your execution, unpredictable executions, and so on. So a whole lot of other problems and messes. So let's see how it compares. The throughput is high. I mean, that single thread is working nonstop. Parallelism, I would say quite none or low. I mean, usually if you want to scale this up to multiple CPUs, you need to spawn multiple processes. It's a bit harder to understand, at least to understand the flow of what's happening there. Development experience can go very bad in some cases, depending how you're structuring your code, of course. The error handling, again, becomes a bit more complex. Debugging, also, I would say an average difficulty here. With the latest tooling, it's a bit more easy. Profiling, again, I would say hard. With the newest tooling, maybe a bit more easy from Google, but it depends on the implementation, of course. Reactive model, I will not go very deep here. I mean, we can have a separate session just about this, but basically what Reactive is this push-based publisher, a subscriber pattern, right? So where something is subscribing to the other thing, right? And it's basically publishing messages from one to the other. So we have this pattern, which is made as a first-level citizen inside our entire code. So all those, all the messages, let's say, that are flowing through this reactive pipes, let's call them, or reactive streams, right? Basically, they how should I put this? They're encapsulating in the various operators across the stream. They're encapsulating the logic to process the data from there. So it's making some kind of abstraction between the actual threads and our code. So our code is encapsulated in those operators. The threads becomes schedulers. Those schedulers are executing those operators, basically. So it's somehow separating our code from the actual threads that sit behind it. Now, what's the interesting part here? This is, you can think of it somehow as the as this event loop, which is basically scaled to multiple threads, right? So it tries to solve some of the problems of this event loop model, like the callback hell one, where in the left you can see the code written with those callbacks. That's Java, by the way. And on the right, you can see the same code written with this reactive streams. So it structures the code quite a bit better. It also introduces new concepts like back pressure handling. Also, so it can handle quite complex logic as well. If you look here, it's doing quite a few complex operations, rather easy. Also, it can signal the end of your execution. And you can use the same principles that Reactive is providing you in order to create different algorithms like fork join, like the Lmax disruptor, and others, basically. So it's quite a powerful thing, but it's quite a complex one. So here in the right, you can see all the elements that are sitting behind this. It's quite hard to explain it in one sentence, right? But basically, that's the whole thing behind the reactive model. So while it brings a lot of benefits, it comes with a lot of complexity, with a steep learning curve. So with the trade-off that Alex mentioned, that okay, if you usually want to use reactive, you need to relearn and re-switch your thinking to this kind of model. Going forward, just to see how this compares. So the throughput, I would say very high. It's high parallelism as well, so it's able to use multiple threads and using them quite to the max. It's hard to understand. It's very often a lot of projects I'm seeing a lot of basically bugs introduced by improper usage of this. I would say development experience is good once you understand it. Error handling, I would say it's still average. Debugging and profiling, I would say quite hard. We have some tooling now with IntelliJ that helps us, but still quite not straightforward. Next one, coroutines. Basically, it's evolving the event loop model once again. The difference here between the event loop model is you can indicate yourself where you want to transfer control to other tasks, right, or other coroutines, how it's called. So I would say that's the key differentiator here. So basically, if in the event loop, this event loop itself was the one having the control and was the one rescheduling or stopping your certain task, scheduling some other one based on some specific points. Here you have more control to say, okay, I want to exit at this point in my execution and yeah, resume something different. With this, you can have you can run millions of coroutines. It's quite lightweight, so it basically simplifies quite a bit the how you're encapsulating your execution context. Your execution context is no longer encapsulated in that megabyte size stack that you had earlier with the thread. It's basically stored in a more lean structure that's specific to your language. One interesting thing with coroutines here is if you were to write, you remember those simple like hello world programs, like you have here the threads, and from each thread you're going to log some message, and then you're executing, and every time the log messages are coming in a different order, right? Remember those? So if you're writing the same with coroutines, all the messages are always going to come in the same order because there's no parallelism going on behind it. I mean, unless you do something to say explicitly, but by default, there's no parallelism. It's only concurrency. So it's going to be predictable, right? Every time it's going to be executing in the same way, depending on how you set up your asyncs and awaits. Okay, let's see. Here the throughput, again, I would say quite high, quite similar to the event loop in most of the things. But I would say it's a lot better in terms of development experience and error handling. It's quite more straightforward. And the last one here, Userland threads. Well, basically this takes, again, the coroutine concepts and builds upon them and says, okay, if coroutines were usually executed on single thread, what if we execute them on multiple threads? Or how they're called here, green threads or fibers, right? It basically implicitly yields control. Maybe that's, so if coroutines were explicit, where you had control to say, okay, please yield here, now it's again implicit. The implementation of these userland threads usually rely on language specifics. So for example, this is found in Go, right? And in Go, it works great. But they try to do the same in C++, and apparently in C++, the benefits are not the same. So it depends quite a bit on language specifics and some deeper implementation details in there. A nice benefit with this is it inherits from coroutines this simpler programming model, this more classic programming model that we are well aware of from like single-threaded programming, right? But still, it reintroduces back some of the problems that appeared with shared resources. So when you had, I don't know, shared memory. So it takes some lessons learned from the other threading models, and it somehow makes some trade-offs between, okay, let's use the threads, let's use the threads more efficient, but on the other hand, we still have some problems that usually come when you use more threads. Okay, from the performance perspective, Userland threads have a quite high throughput. The parallelism is high. They're easy to understand. Development experience quite good. Error handling quite easy. Again, it inherits a bit of the nice parts of each of those, let's say. Debugging and profiling, I would say, still medium because we still have multiple threads behind, so it's not that easy to debug and understand what's happening there in some situations. Okay. Now let's see what Project Loom brings to the table. And I will start here with a quote from Brian Godetz. He says that I think Project Loom is going to kill reactive programming. I don't know. What's your opinion on this? You can write to us in the chat to see if you agree with this or not. But basically, Project Loom. So is it teaching Java Duke to weave carpets with a loom? I guess no. Is it preventing a looming danger regarding Java usage? Or is it attempting to modernize concurrency in Java? 3 questions now. Yeah, of course, obviously the number C is the correct one. So it's attempting to modernize concurrency in Java and to introduce a new threading model in here. So let's look at some of the goals of the project. It aims to reduce the difficulty of writing efficient concurrent applications. It wants to eliminate some of the trade-offs that we have to make when writing concurrent programs, especially the trade-off with complexity and with spending hundreds of hours understanding some new paradigm. They want to ensure an easy adoption. So compared to what they did when they introduced the other types of APIs, now they want to use the existing ones, so don't have to learn other APIs. We don't have to rewrite most of our libraries to use this. So they want to keep some very basic things that you encounter pretty much everywhere, like the thread local and the current thread. They want to keep them still working, compared to Reactive, where basically those are not working anymore and you have to use different concepts. A nice thing here, it's so basically some comparison between the thread and those things called virtual threads that we'll see in a moment. A thread usually has 2 kilobytes of more of metadata, 1 megabyte more of stack. So I told you that megabyte size stack. It takes about between 1 and 10 microseconds to switch between the contexts, while with a virtual thread, it only has about 200, 300 kilobytes of metadata. The stack, it depends on basically what you're executing there. So whatever data you have there, that's basically what is going to be in your stack. And it takes about 200 nanoseconds to execute. Now, from a technology perspective, we have pretty much 3 terms, right? So virtual threads, quite simple. The API there, it's okay, thread, start virtual thread, right? Compared to thread, start thread. Okay, there are some builders, there are some other things in the language that they've added for us to make it easy, but the main concept is that we can very easily create those virtual threads. And the virtual threads are basically the Userland threads that I've mentioned earlier in the threading models. The second concept here is continuations. This is something we're not going to use that much ourselves. It's something that okay, so it's something that it's implicit in the language. Basically, this is used to suspend and resume the tasks. So with the continuations, the language itself, the JVM itself, is gonna suspend and continue your execution and hold the stack in there. In theory, you should be able to write your own continuations to handle some specific cases, but most likely you're not gonna need to. And they've introduced the concept of schedulers, which are basically fork join pools under the hood. Those schedulers are things that are running the virtual threads. And if you go to the next slide, here we can see a visual representation of this. The yellow threads are the virtual threads. And you can basically run millions of those. And the blue ones are the carrier threads, how they're called. And those are managed by the scheduler, right? So basically, those lightweight threads are assigned to the carrier threads. And here we have a new problem that can get introduced. Something called pinning a carrier thread, where basically this, if you can go to the previous slide, please. So basically, this yellow or those orange virtual threads, depending on what they're executing, if they're calling some specific operations that need to deal with I/O specifically, and some specific type of I/O, it will keep that carrier thread, that blue thread, only for itself. And basically, it will start mapping the virtual thread one-to-one with your carrier thread. So you need to be careful what code you write there in order to avoid this, because otherwise you'll just very quickly deplete all your carrier threads. Now, this scheduler is smart enough. It can create additional carrier threads. It can do quite some things. But if you're running millions of virtual threads and you're having this pinning problem, it will just freeze your entire application. And going to the next slides very quickly. Here you have some operators that are friendly with the virtual threads. So things like sleep, like join, waiting for, usually working with sockets. So even this kind of I/O, it's still friendly with virtual threads. And if we go forward, we can see some that will actually pin your thread. So usually things like synchronize. So if you use the synchronize block, if you use open, write, so basically operations on the file part, this kind of things are not yet friendly with the virtual threads. It will pin the underlying thread. Okay. Going forward, yeah, here's some more operations. Of course, I'm sure they're gonna fix those things going forward. At least they are working on it. So one more thing here, it's about troubleshooting. They've added some things for us to detect pinning. So we have a new problem. We need the tools to detect the new problem, of course. And basically, we can generate some different stack traces at the moment. I'm not going to go into the details because maybe those will change until this is going to be released in the full version. But they are working and they are aware about introducing tools for us for this. What is not working at the moment are the thread dumps, the standard thread dumps. So you need some specific tooling in order to execute them, to do thread dumps at the moment. So this means some of your favorite tools might not work that nicely with the virtual threads at the moment. There are some changes in debugger as well. Some things are not working, like pop frame or force early return, especially those of you using IntelliJ when you're debugging. Maybe instead of retrying everything, you're just popping the frame from there. This doesn't really work with the virtual thread. Also, virtual thread plus breakpoints. You need to be careful here how you're setting them, as it can cause some problems and it can pin the carrier thread again. So I'm not going to go into more details at the moment, but just to be aware that there are some problems. So I'm going to stop talking with the theory and let's see the practical. Let's see the experiments from Alex, the mad scientist. Thank you.
Okay, so we ran some code tests. So we wanted to see when Project Loom will help you in a real world application like a web server, for example. And we try to better understand how it works. So basically, virtual threads are Java entities. They're independent of OS threads. These are the fibers that we talk about in the title of the presentation. Virtual threads inherit from the thread class. So it's going to be easy to convert an application to use virtual threads. You just change the implementation of the thread, or you can just change your thread pool and it will start using virtual threads immediately. Virtual threads, like Andrei said, run on carrier threads, which are the regular threads that we are used to. We just now have to call them carrier threads because they are on, they run the virtual threads beneath them. So a carrier thread runs a virtual thread by mounting it. That's the terminology. So it mounts a thread, lets it run, and then it can unmount it. And if the virtual thread blocks, the stack is stored and the virtual thread is unmounted automatically. That's the interesting part. You don't have to do, let's say, a wait. You don't have to put in your code anywhere. The JVM will pause your virtual thread when it's blocked, and the carrier thread will start running something else. And we'll see that in practice. So you can think of it like virtual threads hitch a ride on the carrier threads, and carrier threads are like, I don't know, cars going by them. So when the virtual thread is blocking, it drops off from the car, and then when it finishes the blocking procedure, it then raises the thumb again to be picked up by the next free carrier thread. So first of all, the classic example we all started programming with, I mean, most of us, the hello world. You can print the current thread with, of course, thread.currentThread. And here we can see that the hello loom ran from a fork join pool with the first one, I mean, and it's called carrier threads. By default, the JVM instantiates this carrier threads fork join pool, and it has the size of the number of cores your CPU has by default, and you can increase it by adding this parameter when running the JVM. Okay, next let's see a small example. This is called the wait and hurry example. So what this code does is pretty simple. If the use virtual threads flag is set to false, we will just use the carrier pool. The carrier pool is just is a thread pool with only one thread. I mean, it's defined by the carrier thread count, but in this case, it's one thread. And the task count is how many tasks we will want to run on the pool. So the carrier pool is a pool with one thread, and the virtual pool is a pool that will create one virtual thread for each task, but it will use the carrier pool as its scheduler. So you can explicitly tell JVM which thread pool you want to use as a carrier for your virtual threads. So that is what we are doing here. And the task is fairly easy. It does a 2-second sleep, and then it tries to calculate if a large number is a prime number, and then it prints out the result and the time passed. So let's run the examples and see what happens. So first of all, we will not use virtual threads, so we will have a thread pool with only one thread and two tasks. It will print this and finish in 7.69 seconds. And we can try to illustrate what happened here. So the CPU was idle for 2 seconds during the sleep and then did some work for the first task, which it finished completely. Then it was idle and did some work for the second task. And that's because we only have one thread in the carrier pool. Next, let's see what happens if we still have two tasks, still only one thread, one OS thread, so to say, but we use virtual threads. It finishes in 5.72 seconds. It still used one thread and it still ran both tasks, but it did the waiting part in parallel, because when we started each task, it created a virtual thread for each of them. They were mounted on the carrier thread, started waiting. The carrier thread unmounted virtual 0, mounted virtual 1. That one started waiting. So then the carrier thread unmounted both and was just fiddling its fingers for 2 seconds. And then you see it actually started with the second task first, because that's how it picked it, and then did the work on the second one. But what it did differently here is the waiting period happened in parallel. So you will see the most gain in your app if you have a lot of threads waiting for some time. That's where you will get a performance boost with Loom. Now let's increase the numbers and see, and then we'll see a web server example. The main point for you is to see here that the advantage is the automatic mapping of the virtual threads onto the carrier threads. So we're gonna do 6 tasks and 2 carrier threads. Without using any virtual threads, it finished in 11.44 seconds. And with the same thread count and task count, the only difference being now we are gonna use virtual threads, it finished in 7 seconds and 66. Now we can think of virtual threads as concurrent waiters, so you can wait in parallel. And the real threads are concurrent workers. Now let's see how a web server implementation, a really easy one, works. So here we have a very easy web server implementation. It uses the HTTP server class. It has only one endpoint /test, starts on port 8500. And on the left, it's using a new thread for each request. On the right, it's using a virtual thread for each request. That's the only difference between these two pieces of code. Here it says new thread, here it says thread.start virtual thread. The runnable is identical between them. So like I said, you don't have to write complex code, but the results you will see are as if you have written complex code. So how did we test it? We used JMeter. We are simulating 20,000 users, a ramp up of 20 seconds, and a loop count of 3. That means we get 1,000 calls per second for 60 seconds. And the code has a 6-second sleep. Sorry, I forgot to show it to you. So it just sets some headers on the response, sleeps for 6 seconds, simulating an IO or any blocking operation. Then it sends the response to 100, which means HTTP OK. So that's what this web server does. So let's see the result of the test. First of all is with the DOM threads implementation, so 1 thread per request. It used up to 7,000 JVM threads to run this test, and the CPU load was around 25%. We can see the status is next. It only managed 1.8 thousand response per second maximum, and it had plenty of errors. And as we can see, response time max was 11.5 seconds. And going past 5,000 concurrent sessions, the response time is really bad. You don't want this in your web application. So it also had an error rate of 29%. Now let's see how the implementation with virtual threads ran. It only uses 34 live threads, which is amazing in my opinion, and only 10% CPU load. So it's using the same load from JMeter, but it manages to handle everything really smoothly. On top of that, it doesn't have any errors. It has 2.8K per second maximum responses. And the response times are consistent. Maximum was 7.5 seconds, pretty even distribution, and is not getting much higher as the number of users increases. So now you're gonna say, again, 0% error rate. You're gonna say, why didn't you use a thread pool for the regular implementation? Because no one starts a thread for every request. So I was also curious to see how a thread pool would fare. So I changed the new thread implementation to a cached thread pool, which will submit a task to the executor service for each request. So let's see how this one worked. It used upwards of 10,000 threads, CPU was over 15% compared to 10% with Loom, with virtual threads. Better throughput, but it still had some errors. HTTP host connect exception. And it had maximum of 2,400 calls per second versus a maximum of 2,800 with the virtual threads. And Project Loom or virtual threads had better response times. So Project Loom had 7.5 seconds max, and these clearly get higher as you go past the 10K concurrent sessions. So these graphs have different scale. That's why I added the green line at 6.5 seconds, so you can get a better idea of the difference between them. It had a better error rate, only 0.3%. And yeah, it still didn't beat the virtual threads implementation. So what's the takeaway here? What should we leave home with? So I think Project Loom is delivering on its promise. With simple code change, it's like flipping a switch. Instead of regular threads, you switch your thread pool to a concurrent, you switch your regular thread pool to a thread pool that uses virtual threads, and you should see an improvement in your application's performance. So virtual threads implicitly converts blocking APIs into an async await pattern that you don't even have to be aware of as an user of the API. I mean, as a developer, you should be aware of, at least that it's there, but most of the time it will work just like before, only faster. So when can we get it? When can we deploy it in prod? Well, it wasn't released with JDK 17. So fingers crossed for JDK 18. We didn't get any promises from Oracle, so we don't know yet. But you can download JDK 18 builds with Loom included to run it yourself from that link, jdk.java.net/loom. And you have some more links here, and all the examples are on GitHub. So what do you think? Will you use it? Are you looking forward to it? What's your take on it? We can answer questions here.
Yes, I will use it, or let me rephrase it. Do I need to explicitly choose between threads and fibers? That's maybe it's a stupid one, but do I need in the future? Now, of course.
So fibers is just a word that was used before this implementation comes out. They will be called virtual threads in the future. So the fibers is out, so to say.
Mm-hmm.
But yes, you have to pick one or the other.
Why?
So why? Because the JVM needs to know if you plan on running it as an OS thread or as a virtual thread. The virtual thread can be paused automatically, whereas the kernel thread is a lot more heavyweight, and maybe you want it explicitly.
Okay, but still, why? I mean, why do I need to choose? I mean, in which scenario? I mean,
well, first of all, you have to choose by syntax. When you start a thread, it's called a platform thread in the code or a virtual thread. So you cannot create like a hybrid thread. Maybe that's a good idea for the JDK developers, but currently you can't do that.
Basically, to add on this, if you want to use with the new JVM older things like, I don't know, the standard Tomcat implementation that would use the normal platform threads, it would just work as it is, right? You'd only get the new benefits if you use the specific syntax of this Project Loom, right, to enable it. You can already find projects on the internet that has started rewriting various Spring things with virtual threads, and they're doing various comparisons as well across those projects. So there's already a movement into this direction to embed and get those benefits in the project as soon as possible.
So it's mostly a matter of adoption. I mean, we should feel like in a transition, right? Or
I would say yes. So they put tremendous effort to make it as smooth as possible, this transition, compared to Reactive, which Reactive programming brings pretty much the same performance benefits and concurrency benefits. But there you have to learn something completely different. You have to rewrite a lot of things. Okay, it still brings some benefits extra compared to Project Loom, but the concurrency ones and performance one, here you just get them for free. Just the old code is pretty much working.
Okay, I got it. I'm happy.
Yeah.
This is the bright future.
And we have a question from Gavril Medan. What happens when a blocking call is encountered while executing a fiber? Does it block the underlying thread? The answer is it was in the presentation, but basically your virtual thread gets unmounted. It gets parked somewhere, and your carrier thread is free to execute other virtual threads while you are waiting for I/O. So your carrier thread is not blocked. The carrier thread will continue running different tasks, and when your I/O or blocking call returns, it's like the hitchhikers raising the finger, and then the next carrier thread will pick you up and move you forward, start running the task forward.
Right, and there's another specific question. I think it was at the moment where you were showing those charts.
Yes.
Where is the error rate coming from?
Yes, some were timeouts, and some were also on Windows machines. Unfortunately, you have a limit on how many ports you can use at the same time. So
it's a feature, not a bug.
Yeah, I had issues with it when starting the testing. Then I edited the registries, but maybe it still wasn't high enough. So because the regular implementation was taking too long to reply, even if there wasn't a timeout, Windows couldn't handle so many ports being used by the web server, and it would just throw an error. But that didn't happen with the virtual threads because they were getting parked and done faster, returned faster.
Guys, congrats! You're having a deep knowledge, and the talk was very insightful from my perspective. So
Thank
again,
you.
if I got it, I think everyone else got it. So yeah.
If you're looking at me, if I got it, then that got it for sure.
Yeah, there's also this question from Bogdan. I just don't want to let it unanswered. So it's not just an API over fork join pool. There's also complex logic that defines when a thread will be paused and when it will be resumed without you having to do it explicitly. And it's pretty complex. I don't even want to think about how the JVM guys did it.
Yeah.
Yes, this sort of abstractions help us in the long term focus on other things.
Yeah, they did the complex code so that we don't have to in our apps.
All right, thank you guys. Really nice presentation. See you next time. And we're gonna take another short break, 6 minutes, until we resume with Jakub for the last talk of the day.
Yep. Bye, guys.
Thank you. Bye.
Thank you. Bye.